Okay, so if you're seeing my screen, it says exercises 1 through 6 refer to region R in the first quadrant enclosed by 4x minus x cubed. If you were to graph that, you would see that it hits at 0 and 2. So it's this, you know, you don't necessarily need to know this, but it would do something like that. The first thing though is that usually they just tell you. Usually the problem will say like they'll say like n equals 4 from 0 to 2, and then a more standard problem would be like LRAM, for example. Now, do you know if you're going to be expected to sketch the rectangles? Or
probably, yeah.
Probably, okay. So the challenge here is that you really need to kind of zoom in on this. So let me do a bit more here to actually, let me go ahead and just graph it in another tool and see if I can give you a better window to actually make these things. Yeah. So let me snip this. All right. So the left sum, or LRAM, means that you use 4 left points, but my approach is a little bit different than maybe what you've seen in class. The first thing I would have you do is find your delta x. Your delta x is b minus a over n, 2 minus 0 over 4, which is 1/2. And I would actually have you start at the left bound, and I'd have you write out like go up by delta x. Okay, and you can see there are 1, 2, 3, 4, 5 points. For an LRAM, you're going to use the 3 on the left, or 4 on the left. I'm sorry. So you literally like, and the first one's a little bit awkward because you go to where you hit the curve, and you hit the curve right there at 0, and your width is, oh, why did I graph the right thing? I did not. Like, why isn't this working? So let me make another picture. It's not that much different, but let me actually get the right picture for you. Okay. So at 0, you literally evaluate the function at 0, or in this case, where does it hit the curve at 0? And then it's got a width of delta x. So this has, and it's a little bit awkward, as a height 0 and a width of delta x. But then you go to 1/2, which is right about here, and you go up to wherever it hits the curve. Okay. Now, if you're not sure where it hits the curve because your graph isn't like this, you would actually evaluate the function at 1/2. You put that in. But for our purposes, you hit it, and then you go right delta x. So the height here is f of 1/2, and then the width is always delta x. And then you do the same thing at 1. You go up and you hit the curve, and you go over to whatever your width is. This time it looks like it might actually overlap. Boom, like that. Delta x. And so that height there is f of 1. Like you would put 1 into this function. And then the last one, you've got to have 4 rectangles. That's what the n tells you. You go up and hit it wherever you hit it on the graph, which again will be f of 3/2 this time. And even though I'm going over to the right here, that's still correct for this. And is that okay? Is that clear?
Yep.
Great. Now, to actually calculate LRAM, there is a formula. The formula is you take your delta x, and then you evaluate the function at a, which is the leftmost endpoint. And then depending on your book, it will say something like a plus delta x plus f of a plus 2 delta x, and so on, all the way until you're done. And this formula may or may not be very helpful, but when we actually put some numbers in, your a is 0. So you're evaluating the function at 0. Then 0 plus delta x, 0 plus 1/2 means you're evaluating the function at 1/2. See where that next point is, plus f of a, so a is 0. 2 times delta x, 2 times 1/2 is 1. So that becomes f of 1. Look, that's the third point, plus f of 3/2. So from here, you have to evaluate that original function. Your f of x is 4x minus x cubed. So you have to do that at each of these points. So like the first one is 0. Second one is 4 times 1/2 plus 1/2 cubed. The next one is 4 times 1 plus 1 cubed plus 4 times 3/2. I'm sorry, these are minuses, not pluses in here. Sorry about that. Minus. And then actually that's 4 times 3/2 minus 3/2 cubed. And you get some number out of that.
Mhm.
Okay. So we've chosen sort of an awful function for this, because like these are a lot of work here to do this. I would recommend choosing a nicer function if we're actually going to work these out, because this becomes cumbersome down here to do, but it's totally doable. So if you're okay with that, I'd like to pick a different function for RRAM.
That's fine.
Okay. So let's say f of x equals 1 over x, and we're going to go from 1 to, I don't know, let's go to 5, n equals 4. Actually, let's go 1 to 9. N equals 4. All right. So the way I would start this is I would always calculate delta x. Delta x is b minus a over n. 9 minus 1 over 4, which ends up being 2. And I'm going to graph it. I'm going to kind of cheat here by having this available, but you really, I mean, I think you know what this graph looks like. It goes down and to the right. Having that really does help a little bit here. And then let me go 0. Let's go 0, 2, 1. It's not enough, but okay, right in there. All right, so let me snip this in, and I'm doing it on the tool because it just makes drawing the rectangles easier. So this time with RRAM, you actually start all the way to the right. Okay, so in this case, all the way to the right is your B value, it's 9. You go up and you hit it. Wherever you hit it, that's your, and then you go left this time. It kind of feels backwards, but that is what you're doing. So that's your delta x. Oops, our delta x is actually 2 in this problem. So you actually go over 2. That's your delta x of 2. Your height here is y equals 1 over 9, because you put 9 in. And then you go to 7, and you hit it again. And again, you go left 2. Okay, so it's delta x here. It's 2. The height is y equals 1 over 7. And you keep going until you hit the number of rectangles. We need 4. Okay, so there we're hitting it there. And going right or left 2. Delta x is 2 again. Height right here is 1/5. And then the last one, you hit it there at 3, and you go left. You go left 3. So delta x equals 2, y equals 1/3. Okay. And this would be your RRAM, because you're starting from the right.
Mhm.
Okay. Now, just before we carry on here, is this an underestimate or an overestimate? And if you're not sure, let me know. I can explain.
Underestimate.
It's an underestimate. All right, great. Okay, so RRAM here, it's the delta x, and this time you're actually really starting over here on the right, the f of b, and then you kind of work backwards. It's f of b minus delta x f of b minus 2 delta x and so on. I don't really like this approach. What I prefer doing is once you know the delta x, you start with your left value, which is 1, and then you go up by delta x 3, 5, 7, 9. And then I like to just circle the ones that I'm using depending on the problem here. So the problem here, we're going to use those. So our delta x is 2, and we're going to do f of 3 plus f of 5 plus f of 7 plus f of 9. And you can see that these are, the values that we have along here. It's going to be 2 times 1/3 plus 1/5 plus 1/7 plus 1/9.
Okay.
All right, and then we'll do an. I think did you have midpoint also?
Yeah.
Okay, so let's do midpoint with this one. We'll go again. We'll go n equals 2, and we'll go from 1. No, that's not going to work. We'll just do n equals 4 again, and we'll go 1 to 9. So your midpoint, your delta x is again, it's the same as before. It's 2. B minus a over n. It's the same each time. When you make those points, though, now you need the midpoint between these here. You need 2, 4, 6, and 8, and those are the values you're going to use for this. And this one's slightly different because you hit the curve. You go to 2, and you go and you hit the curve. Okay, but then you go left, and then you go right. Okay, so I actually shouldn't even have drawn that middle line there, and I will erase it. But you can see that you get some over and some under. Like there's like that part's an over, but then you got to compare that to here. But its height right here is f of 2. Okay, and you do the same thing at 4. You go and hit it, and then you go left, and you go right, and you get that rectangle there, and that's f of 4. And then what was the next one? 6. You hit it, and you hit it. You get that right there. And you do the same thing at 8. Now, a harder question to answer is whether this is an underestimate or an overestimate. You probably would not be asked that because it's pretty tough to actually figure out. But compared to the other ones, this is actually a better estimate because you get like some of this area is really this area. Some of this is really this area. So this one's even better than a left sum or right sum in most cases. So your MRAM is delta x. I'm gonna switch color here, which is 1/2, and then it's f of 2. So that's 1/2 plus 1/4 plus 1/6 plus 1/8, and you get some number for that. Is this all familiar to you now that we've looked at it again?
Isn't delta x 2?
Say that again.
Isn't delta x 2?
Yes, thank you. Yeah, it is 2 minus 3 for me for not paying attention to that. Do you have a calculator part of this exam, or is it all by hand?
Not.
Okay. All right. So, I mean, that's kind of it for left sums, right sums. They're more often approached in calculus 2. So, okay. Can I move on to another problem type?
Yeah.
All right. So this is, and there's probably a better example, but they will give you something like this, and they will ask you a bunch of questions. It'll be like A, B, C, D. And like, we should just go through some of the properties to make sure you know what to make of these. So they will ask you like, what is the integral from 2 to minus 2 f of x dx? And you will notice that it's kind of like this one. Do you know the answer?
It's -4, right?
It's -4, yes. And then they might ask you, for example, what is the integral from -2 to 5 f of x dx.
That's 7.
4 plus 3 is 7. And then they might ask you what is, and I'll copy those down again. They might ask, what is the integral from -2 to 5, 3 f of x plus 2 dx. This is where maybe there's something new.
That would be 7 times 3, 21 plus 2, 23.
So this 2, the antiderivative of 2 is really 2x. Do you remember that from like if so you're really supposed to separate these. It's supposed to be 3 minus 2 to 5 f of x dx plus integral -2 to 5 2 dx. And yes, the first one is absolutely 7 times 3. Okay. But this one on the right, there's a couple of ways you could do it. You could use antiderivatives, and the antiderivative would be 2x, and you would evaluate at the endpoints. The other, like the way that they want you to do it when you're at this part of the course, is they want you to realize that it's 2 going from -2 to 5. So it's really a rectangle here. So it's kind of the same thing. It's +2 times 5 minus a -2. So what is that? 7. So it's 2 times 7. So you get 21 plus 14.
Okay.
You may have to write all these steps though. And I mean, like it's one of those things where like after you know the derivative and they say, oh, use the difference quotient, you're like, why would I ever use the difference quotient? But in this part of the course in your retake, you may find that you have to do that. Okay, so let me give you another type of problem you might see. They might ask you for the integral from -2 to 5, 2 g of x plus x dx. I'm going to give this one a try.
So that's 2 times 2 plus x squared over 2 from -2 to 5.
Yes, that sounded very good. And you could figure that out, I guess. That would be, whatever that ends up being, right? Okay. Sorry to ask this, because I should have asked it earlier about the LRAM and RRAM, but let me snip it in. So you can also get an LRAM, RRAM where they give you a table. Do you remember if you had that in your original test?
I don't remember if it was on the test, but I've definitely done those problems before.
Okay.
So it might have been.
Okay. So let's do real quick. Let's do an LRAM on this. I know we're jumping back. And let's go from 0 to 30. N equals 1, 2, 3, 4, 5, 6, n equals 6. Okay. And what you do is you treat, this is your X and this is your Y. You first calculate your delta X. Your delta X is going to be 30 minus 0 over 6, which is 5. And that syncs up really nice to this. We're not doing trapezoidal rule. We'll do LRAM. So for LRAM, you're going to use these ones here. And since you need 6 rectangles, 1, 2, 3, 4, 5, 6, you got it. So your LRAM is going to be delta X 5 times, and then it's the Y values. 2.5 plus 2.4 plus 2.3 plus all the way up to 2.5. And then RRAM, how would that be different?
RRAM goes from the right, so it starts with 30 and ends with 5.
Right, and use these. So it's like one use this and one use this. And they could obviously go up all the way if they wanted. Trapezoidal rule, do we need to cover that, or do you think that that is excluded?
It's on the test.
It is. Okay, so let's do this with trapezoidal from, I'm going to recopy down. Let's go from 30 to 60. And we'll go n equals 3. N equals 3. All right, so your delta x is slightly different here. Do you remember the trapezoidal rule? It's slightly different than the others.
It's essentially just a trapezoid made from the 2 points.
Yes, but in terms of the way you do the formula. So let me snip it in here, and I'll just explain it. So here's the trapezoidal rule. So instead of it being delta x on the outside, it's delta x over 2. So that's a really small thing. And there's a reason, but if we don't care about why, you take the left endpoint and use it once, the right endpoint and use it once, but every other thing in between you use twice. So in your problem that I gave you, your delta x is going to be 60 minus 30 over 3, which is 10. And you're starting at 30, so it'd be 30. Wait, why is this not working? Oh, because it starts at 0. I see. So 30, 40, 50, and 60. So your delta, your trapezoidal sum is delta x, which is 10 over 2. And then you're going to do f of 30 plus 2 times f of 40 plus 2 times f of 50 plus f of 60. So you just use that endpoint, the 2 endpoints one time. So it's 5 times 2.6 plus 2 times 2.4 plus 2 times 2.4 plus 2.3. Okay, so the only difference is that you're dividing by 2 on the outside, and you use all the points in your window here, but you double up on the in the ones. And the reason is, you probably saw this in classes, when you draw these trapezoids, you double up on the height here, like use it again when you make the next one, and then use this one again when you make the next one. But the last one you only use that height one time.
Yep.
Okay. I strongly recommend memorizing and not trying to figure it out on the fly, because you'll miss it divided by 2 or something, and but if a good exam will have both answers there to check if you're paying attention to that. All right. Okay, so now back to a steady dose of just integration problems. These are not meant to be difficult at this point, but when you first saw them, they were you maybe weren't even sure how to proceed with some of them. But my guess is now you're just going to know them really, really quickly. So like this one here, how would you proceed to do this if the question said to determine the value of the integral?
Well, it might be easier to start by writing the x's, instead of 1 over x squared, it's x to the negative 2.
I agree. I call that a rewrite step. Okay.
Which would make it negative 4x to the negative 1.
Yes. So yes, it's so this part is negative 1 over, is however you want to do it, but yeah, it becomes negative 4 over x, and you evaluate from 1 to 2. Okay. And if you're not comfortable with your fractions, you will be after you do this, because this one looks bad at first, but it's negative 2 plus 4, so it ends up equaling 2.
Mhm.
All right. So I'm going to send you in the chat a table of derivatives and integrals. There used to be books of these, and maybe I've already told you that. I just want to focus in on the ones that are common, and I guess ask you if you think you're going to get anything outside of this list. Like, are you going to get arctangents? Are you going to get inverse, sine, that kind of thing? Like, do you have any idea what what kind of problems your instructor tends to emphasize? Because these are basically all variations on the power rule in this first section, and from what I sent you, that's on page 2. These are basically all what I would consider power rule types, except maybe the last one here.
I don't think there's going to be too many girls that are that complicated because the next chapter is the one that focuses more on
Right.
evaluating different types of derivatives.
Right.
Integrals.
So then you get into trig functions, and this top grouping, like these are for sure, like you got to know these really, really well. Like these are like fair game, but then everything else, I don't know. That's where like, is it worth studying because you might get one? I don't know. I don't know what to tell you. The inverse trig, though, these do come up, and I don't know why instructors like these so much. But they seem to really like them. So on the third page, there's these inverse trig ones. I'm doing this because it seems to go ahead better with this. So I saw a problem on your review here that seems like it would fall into that category. Yeah. Nope, it does not. So where is that? I guess maybe chapter 7 is where it starts getting like heavier, but like this one in the middle here, like you could see something pretty reasonably, like, let me give you an example. Let's go 0 to pi over 4, 1 over 1 plus x squared. Maybe there's a 5 here, dx. So this is really 5 arctangent of x evaluated from 0 to power 4. And you said you probably won't get this, but I mean, this is the kind of problem that if you don't know these, you have no chance. You just can't do them.
Mhm.
So, all right, so let's do a few that maybe are unclear, but not like this, and just see if you're really comfortable with them. Okay, so here's another problem from your review. I'm choosing evens because you may want to go back later on and work on the odds on your own. How would you approach this problem?
Maybe just start by expressing everything as a square instead of a square root.
Okay, so like what I heard, and you can correct me wrong, is like maybe writing it this way.
Yeah.
Okay, and you can apply exponent properties for this. Okay, so this becomes 1 over t to the 3/2 power. And then you might even want to say, okay, well, let me make it t to the minus 3/2 power. And you're going to evaluate that from 1 to 4 dt. Okay, so if that's okay, then when you use the power rule here, you add 1 to the exponent and you divide by the new exponent. So these match. Now, if you're really fast, you might even be able to flip this and make this negative 2t to the minus 1/2. But if you can do all that, maybe you even move it back down to the bottom, negative 2 over t to the 1/2. And maybe you even say, oh, well, I might as well write it as, let me come up here, negative 2 over the square root of t. And you evaluate that from 1 to 4. The reason you would do this is this is probably easier to evaluate than exponents.
Mm-hmm.
So this becomes -2 over the square root of 4 minus -2 over the square root of 1. So we have -2 over 2, -1 plus 2, which equals 1. Should the area under the curve be positive or negative? The answer is it depends. Most of your textbook problems are designed to be positive, but I see that we probably should look at another type of problem where it could be the case. That's not. So it's kind of a similar variation to this problem here. Let me grab this. So you could be asked something like this. X squared minus 3 divided by x dx. You could be asked to do something like this. And at first glance, it would seem like there's no way to do this, but if you apply algebra, and specifically its exponent rules tends to be the ones that you're using the most of here. This is like x squared over x minus 3 over x. So this becomes the integral from 1 to 2 x minus 3 over x dx. You may also have to multiply binomials or FOIL, or it could be some even factoring. I really couldn't tell you, but if you can get this far, they're just power rule problems, 1/2 x squared. But this one though, the integral 1 over x dx is the natural log of the absolute value of x. So is that okay?
Yeah.
All right. So that becomes -3 natural log absolute value of x, all evaluated from 1 to 2. You do not have to separate these, and you might have been doing that when you first learned this. Like you can just evaluate the integral all together like this if you want. So that's 1/2 2 squared minus 3 natural log absolute value of 2 minus 1/2, I guess I'll put those parentheses, 1 squared minus 3 natural log absolute value of 1. All right, so this becomes 4. 1/2 of 4 is 2. 2 minus 3 natural log of 2. This is 1/2, and natural log of 1 is 0, so it becomes -0. So you got 4 halves minus 3 minus 1/2 becomes 3 halves minus 3 natural log of 2. That's your final answer.
Okay.
All right. The 28, we'll do this, and then we should do these kind of other questions that I see here. All right, so this is a U substitution problem. And I don't know if you don't know this yet at this point in the course. I'm not sure why they have it here, other than they probably think like you can be like, oh yeah, the antiderivative of sine is minus cosine, and then the derivative of the inside function is -2x, and that goes with that. So like somehow you're supposed to do this, but it's really a U substitution problem. But you're not supposed to know it. So if you came off to the right here and said, oh, U is 1 minus x squared and du is -2x dx, you may be marked wrong for that. So just keep that in mind. Like maybe ask your instructor when you're taking it, or say, hey, is it okay if I use this approach? And please tell me if any of this is foreign to you. Is this
It's familiar.
I mean, because there's a lot of U sub in chapter 7, I think.
Yeah, it's in chapter 7.
But here you can see like you don't know that yet. So it's kind of a guess and check approach. Like it's like, well, what's derivative gets you back to this one, and this one does work out. So you evaluate from -1 to 1.
Okay.
All right. So moving on here, let me go look. I was looking for some problems where this 54 is one we need to look at. I know this is like really favorite of instructors on this test. So they give you a graph, and they tell you, okay, this is a semicircle and this is 2 line segments, great. And then they give you, they say this is given, and I'm gonna put that over here on the right. They tell you that g of x means you take the integral from 1 to x f of t dt. So for example, if we want g of 0, that means that x is 0. I'm sorry, we can't do that. Let's go g of 1 for the moment. That means it is the integral 1 to 1 f of t dt. And it's literally asking for the area right here, which is 0. And that was a property we didn't cover earlier, but when the bounds are the same, the area is always 0. Now let me go to the one that I was starting to do here. G of 0 means the integral from 1 to 0 f of 0 dt. f of t dt. All right, so take a look at that, and keep in mind what this is asking for. It's asking for the area between 1 and 0 on this curve. So it's asking for this area right here. But do you see how the bounds are basically backwards, the bottom? So when it's backwards like this, the area above the curve is actually negative, and the area below the curve is positive. Okay, and if that's not clear, I would like to clear that up with another example. But do you remember hearing about stuff like that?
Yeah.
At some point? Okay. Okay. So let's actually do some questions here where it's reasonable. Because not that one wasn't, you wouldn't get something like that in the exam. But let's pretend like you were given this question right here. Find g of 3. So g of 3 means the integral from 1 to 3 f of t dt. So if I were to draw it, it's the area of this triangle right here. And so there's no antiderivative. It's just purely like, can you find the area of this geometric shape? Area of a triangle is 1/2 base times height. The base is 3 minus 1, and the height is 1. Okay, so this ends up being an area of 1. Okay, but this is important. It's below the x-axis, and since we're going with the standard like direction here, when you're going where the top number is actually bigger than the smaller number, below the x-axis is negative. Okay, so the answer here is actually -1. Now you could have gotten that by telling me the height was -1, but I don't like mixing like real interpretations of height. Height is always a positive number. You don't tell people your negative height. You say I'm whatever your height is. So I like to like apply it at the end. Okay, but now like if I asked you for the integral from 3 to 1 f of t dt, I know you can just tell me it's the negative of this number, but if you look at, because you're going backwards now, and the area is below the axis, that's why it's positive. All right, so is that okay? Is that clear?
Yep.
Great. So there's, as you know, there's no body language for me to like see that you get it or don't get it. And I'm really relying on, hoping that this is clear and helpful to you. So we're gonna find g of -1. I'm actually gonna snip in the graph again. All right, so g of -1 means the integral from 1 to -1 f of t dt. So again, notice this is going backwards. So that means areas above the x-axis will be negative. Okay, and if I carve out this shape here, we know that this is a semicircle, so this right here would make a quarter circle. So your area of a circle is pi r squared. So here it's pi r squared, but you divide it by 4 because you only need a fourth of it. And your radius in this case is any direction you want to go, but your radius is 2. So it's pi 2 squared over 4, but it's negative because of the whole discussion we've been having. Okay. Let me grab the AP examination prep question. Let's just look at this last one. It's very similar to this. All right. So this time, again, it goes from 1 to x. It doesn't always go from 1 to x. Like I would sort of prefer it go from -2 to x because then it starts here. But they're choosing to kind of break it right in the middle, which I mean that number could change. So g of 4 in this first example means the integral from 1 to 4 f of t dt. So you're finding the area from 1 to 4 now. Now notice some of it's above the x-axis and some of it's below. So areas above are going to be, that's terrible. They're gonna be positive, and areas below are going to be negative. And because of the geometries here, like this is a trapezoid, this first one, this is a triangle, this is another triangle here. So you want to be able to come up with each of those areas. I'll remind you the area of a trapezoid is 1/2 B1 plus B2. The bases are what are parallel times the height. So we got 1/2 3 plus 1. Height is actually this way, which is a little bit odd. That's the first region, plus 1/2 base times height, minus 1/2 base times height. So whatever this adds up to, what do we got here? Just 2. 4 divided by 2, we get 2, because these cancel.
Okay.
All right. So g of -2 is going in the other direction. I'll just point out that you're going, it would be all of this here, and you'd have to come up with that. Since it's going left and it's above, it would be negative. All right, so let me slightly modify this problem and ask you some questions that I think you might actually see on the test. I know we're coming to the end here, but let's see if we can sneak this in. All right, so this time we're going to let g of x equal the integral from -2 to x f of t dt. Okay, so we're starting here. Okay, and I could ask you, where is g of x a max? And you can tell me what you think or don't think about that question if you understand it. If you don't, I'll explain, but go ahead and let me know.
Probably.
Try one more time. So g of x represents the area under the curve starting at -2. So if I said, where is the area the greatest? You could probably answer that question. So let's say we went from -2 to -1. Does this area contribute positively or negatively to the area?
Positively.
Positively. And if we go to 0, it continues to contribute positively, right? And then we keep going and so on. So see how all the way up to here contributes positively?
Yep.
But once we cross this threshold, it contributes
Negatively.
negatively. So we would go to the point where it stops helping. So similarly, we could ask where is g of x a min? Okay, and this one's a little bit harder. So notice that g of x is initially 0. Like if you say x equals -2, that's the integral from -2 to -2 f of t dt. That's 0 by definition with the same bounds. But if you go to the right, like this, all of this is positive, and then you take a little bit away here, is 0 still smaller than like whatever this adds up to minus whatever this adds up to?
In this situation, yes.
Yes. But if I gave you a different graph, like if I told you that it was, if this was the graph here and this is -2, and then it comes up and this is 2, all of this area contributes negatively. So the min would now be at x equals 2. Because right at that point, you stop counting negative areas, and then you go to positive areas.
Mhm.
All right. So that does take us to the end of our lesson today. Do we have another lesson scheduled this week, or is that it for now?
I think my mom might have scheduled another one, but I'm not sure.
Okay, yeah, I thought I saw so we'll just pick up here next time. I'll send you the notes and the screen recording out shortly, and have a great day.
Thank you. You too.
You're welcome. Bye now.
Bye.